Did you know that not everyone believes in climate change? Climate change is a complex issue. It's uncertain, it's invisible, and it's a long-term threat. So it is the subject of quite a bit of misinformation. A small Christian Pentecostal church, not mainstream, based in New South Wales, argues that climate change is not possible. It's simply part of God's plan or God's divine intervention. One specific misconception is that climate change is just part of God's natural cycle on Earth. While the Earth's climate change has fluctuated in the past, the rapid warming observed in recent decades is primarily due to human activities. This releases more carbon dioxide and other greenhouse gases into the atmosphere. So no, climate change is not just natural variation. But why does this view persist? Motivated reasoning plays a significant role because God's divine plan governs the Earth's climate. This leads people to accept only evidence that aligns with this pre-existing belief, reducing the cognitive dissonance experienced when confronted with contradictory information. Confirmation bias also reinforces this stance by driving them to seek out information that supports their existing belief and dismissing evidence that challenges this view. System justification further contributes to the skepticism, as the congregation may feel powerful to effect change and are more inclined to defend their current system. Finally, the Dunning-Kruger effect exacerbates this disbelief because there's limited knowledge about climate science. They overestimate the understanding of the issue, believing they know as much or more than the experts. This overconfidence in limited knowledge leads them to reject expert consensus and reinforce existing beliefs and skepticisms. Detection and attribution is the process used to determine whether observed climatic changes are naturally variable or if they're attributed to human activities. The confidence in attributing this to human activities has grown over time. From between 1990 and 2022, the Intergovernmental Panel on Climate Change moved from no evidence to unequivocal proof. This is because climate models show us a comparison of our observations using paleoclimate proxies and established baseline data, so we can simulate how different factors such as greenhouse gases with and without human activities impact this natural baseline. When combined, human influences closely match the observed temperature changes. So by systematically comparing models and observations, we can confidently attribute recent climate changes to human activities. Natural variations have occurred throughout Earth's history. Instrumental records, which are direct measurements of climate variables like temperature using a thermometer, are only available for the last few hundred years, but we can use proxies, which are natural recorders of historical climate information. So if we look at this graph on the screen, this is carbon dioxide concentration alongside temperature variations for over 150 years. The historical data was obtained from ice cores and tree bark rings, which contain isotopic information that reveal climate composition and temperature. So ice layer counting, dendrochronology, radiocarbon dating, sediment layer counting is what has allowed us to reconstruct past climates. Climate drivers are factors that have a significant but predictable influence on climate and weather patterns, and they're a way that scientists are able to predict long-term climate trends and their impacts on local and global scales. So these drivers influence weather patterns over weeks and months and are based on large-scale phenomena such as sea surface temperature and pressure anomalies. Together, these anomalies alter the strength of circulation cells, which are responsible for large-scale movement of air and impact the weather systems over a wide area. These anomalies impact the immediate region, but also have far-ranging effects on the global climate system. For example, the Southern Annular Mode, Indian Ocean Dipole, and El Niño Southern Oscillation have significant knock-on effects for the climate in Tasmania. Climate change models are tools used to understand and predict future climatic conditions. It's impossible to have meteorological measuring stations at every surface location and level of the atmosphere across the world, so we rely on models to simulate the atmosphere using data from sources such as thermometers and rain gauges. Although the initial 1970s models were very basic, the modern ones are very sophisticated and they include a multitude of high-resolution factors, even down to 5-kilometre grid squares in Tasmania. So unlike weather models, climate models help scientists understand the potential future climatic conditions and make informed decisions about mitigation and adaptation strategies. As future emissions are not clear, climate scientists have formulated a range of possibilities known as representative concentration pathways. Each of the 4 RCPs represent a change in energy at the top of the atmosphere in watts per metre squared. This model shows us the projections of global surface temperature changes under different emissions scenarios between 1900 and 2100. So you can see the black line, that's the historical global surface temperature changes, with each other line indicating a model mean global temperature for a certain emission scenario. In this case, red is high emissions, blue is low emissions, and orange and light blue indicate moderate levels of emissions. This tells us that if high levels of greenhouse gas emissions continue, the global mean temperature is projected to rise as much as 4 to 5 degrees above pre-industrial levels by the year 2100. This is compared to a projected 1 degree rise for low emission scenarios. So the higher the increase, the more severe global warming impacts on climate, weather, sea levels, and ecosystem. A climate tipping point is a critical threshold where a small change in the climate system can lead to dramatic, irreversible changes in a system's state. These tipping points are driven by positive feedback loops that amplify changes once certain thresholds are crossed. Tipping points are linked to dangerous climate change because they can cause large-scale impacts on both human and natural systems. For example, the ENSO disruption could lead to more frequent and severe weather events globally. Predicting tipping points is challenging, and often they're only recognized once they're imminent or have already occurred, although ideally predictions could be made based on paleo records and climate models. Identified early warning signals would indicate signs of instability such as increased variability and slower recovery from disturbances. A tipping point is a critical threshold where small changes in the climate system can lead to dramatic, irreversible changes in a state system. So this is essentially linked to dangerous climate change because there are large-scale impacts on human and natural systems, such as an ENSO disruption could lead to more frequent and severe weather events globally. All of this gives us the impacts of climate change that are split into 3 categories. Physical evidence of human-induced climate change includes sea level rise, extreme weather events, glacial and polar ice melts, and ocean changes, as described here. In terms of biological impacts and evidence for human-induced climate change, we've got changes in ecosystems, marine life, terrestrial life, and forest. And finally, our human system impacts, or evidence for human-induced climate change, are impacts on human health, animal health, plant health, agriculture and food security, economic impacts, migration and displacement, and our water resources. So in summary, we've got a copious amount of scientific evidence that shows us that climate change is in fact not a natural variation and it is human-induced. Thanks so much for coming along today. This is our reference list. On the next few slides, feel free to pop any questions down below and I'll get back to you. Thanks.